It is in the nature of humanity to seek understanding and decipher the mysteries surrounding us as precisely as possible. What applies on a small scale can naturally extend to the grander picture. For generations, astronomers have strived to comprehend the vastness of the cosmos and its countless features. Yet, researchers face a significant hurdle. From our earthly vantage point, it is impossible to observe the entirety of the universe. Does this optical limitation mean that we will never reach the end of the universe? And does such an end even exist? Let us delve into this intriguing topic. But before we begin, remember to leave us a like and subscribe to join us in exploring the greatest secrets of the cosmos. Our view of the stars is limited. The thousands of celestial bodies twinkling in the night sky are but a fraction of the cosmos. The region of space visible from Earth is aptly named the observable universe. According to the cosmological principle, the universe appears the same to all observers, regardless of location or direction of observation. Consequently, there exists a spherical space around Earth, the volume of which defines our cosmic field of view. The optical barrier that restricts our perception is termed the observation horizon, encompassing the cosmic area from which light and information have reached us since the Big Bang. While the universe's birth occurred approximately 13.8 billion years ago, this does not mean the observation horizon is 13.8 billion light-years away. The universe's continual expansion has extended distances, resulting in our galactic line of sight being approximately 46.6 billion light-years away. With this context, it becomes evident why fully decoding the universe is often considered an impossible task. To address whether it is feasible to reach the end of the universe, we must first confront a more fundamental question: does the universe even have an end? Can a construct often referred to as infinite possess a defined boundary? The answer to this question remains elusive. The shape and volume of the universe are still enigmatic. Theories range from a spherical cosmos to a flat, infinitely large expanse, and even to more unconventional geometries like a donut or a trumpet shape. Moreover, an important distinction must be made between infinity and unboundedness. Even if the universe has a finite volume, it does not imply it is unbounded. To illustrate, consider the often used analogy of an ant on a balloon. If the ant moves across the balloon's surface, it could traverse endlessly without encountering an edge, perceiving the structure as infinite despite its finite nature. While simplistic, this analogy helps conceptualize how the universe might lack a boundary despite being finite. However, unlike the balloon, the universe is not embedded within a higher dimensional space. Some researchers affirmatively state that the universe does have an edge or an end, though their reasoning is complex. This conclusion stems from the theory of chaotic inflation, introduced in 1986 by Russian cosmologist Andrei Linda. According to this hypothesis, our cosmos is merely one link in an infinite chain of sub-universes. The majority of the multiverse expands perpetually in an inflationary manner since the Big Bang, with localized areas halting expansion to form bubble-like partial universes. Each sub-universe could possess distinct natural constants and physical laws. Theoretically, interactions between individual universes are possible. However, the notion of an end does not pertain solely to spatial boundaries but also to the existential fate of the cosmos. The Big Crunch, Big Rip, and Big Freeze scenarios offer different interpretations of how the universe may ultimately conclude. Currently, the most widely accepted scenario is the Big Freeze. As the universe's expansion accelerates, driven by dark energy, galaxies grow increasingly distant. Eventually, photons will be redshifted beyond recognition, and star formation will cease as gas reserves deplete. Existing stars will extinguish, leaving a dark, cold cosmos. If protons decay, even the remnants of stars will vanish. Black holes will evaporate via Hawking radiation, and the universe will reach thermodynamic equilibrium, marking its heat death. Despite this grim prognosis, human curiosity compels us to ask, what happens after the end? While an end typically signifies finality, some experts propose that the cosmic end may herald a new beginning. This idea aligns with the Big Bounce hypothesis, which suggests that the universe undergoes a perpetual cycle of contraction and expansion. Rather than the Big Bang marking the beginning of space-time, it could represent a transitional phase from a preceding contraction phase. If this is the case, time may have always existed. Remote regions of the universe could have interacted, forming a homogeneous cosmos where the microwave background radiation, a relic of the universe's early days, balanced out. The Big Bounce challenges conventional cosmology but gains traction among researchers. It posits that as the universe contracts into a dense state, a new expansion phase begins, setting the cosmic cycle in motion again. This theory raises intriguing possibilities. Could our universe be one of countless cycles? Could another Big Bounce occur in the future? The Big Bang remains the cornerstone of cosmology, supported by evidence such as the cosmic microwave background radiation, CMB. However, even the CMB raises questions. It appears isotropic, showing no significant variations, even between regions that could not have interacted in 13.8 billion years. Inflation theory addresses this by proposing a period of rapid expansion that smoothed out these discrepancies. Still, the mechanism behind inflation and its eventual cessation remains unexplained, prompting scientists like Paul Steinhardt to explore alternatives. The Big Bounce offers a fresh perspective, suggesting a universe with no definitive beginning or end but a continuous rhythm of renewal. Time, under this view, could be eternal, with countless cycles preceding and succeeding our own. The Big Bounce hypothesis is not merely a theoretical exercise but also a profound challenge to the conventional notion of a singular beginning to everything. If the universe exists within an eternal cycle of contraction and expansion, then the concepts of a first moment or a final fate become irrelevant. Instead, we are left with a cosmos that is perpetually regenerating, a universe that is both ancient and young, depending on where you look within its cyclical timeline. This idea also opens the door to questions about memory and information across cycles. If the universe undergoes repeated bounces, could information about the previous cycles be encoded in the fabric of the cosmos? While this notion seems speculative, it aligns with research into quantum mechanics, where information is theorized to be conserved. Some physicists speculate that echoes of past universes might even be discernible in the cosmic microwave background radiation, albeit faint and challenging to detect. The Big Bounce hypothesis also has philosophical implications. It redefines our relationship with time and existence, suggesting that our universe's story is just one chapter in an infinite series of cosmic sagas. This perspective can be both humbling and liberating, as it implies that the universe does not rely on a single event for its existence but is instead part of a larger, timeless process. Despite its allure, the Big Bounce remains a topic of intense scientific scrutiny and debate. Observational evidence for such a cycle is scarce, and the model faces several challenges. For one, the physical mechanisms that could halt a contraction and initiate a new expansion are not well understood. Furthermore, the theory must contend with the entropy problem. In an eternal cycle, entropy would theoretically accumulate, leading to a heat-death scenario after countless bounces. Proponents of the Big Bounce argue that quantum effects or unknown principles of physics could reset entropy levels, allowing the cycles to continue indefinitely. Another contender for understanding the universe's ultimate nature is the multiverse theory, which often intersects with the chaotic inflation model. In this view, our universe is merely one bubble among an infinite array of others, each with its own laws of physics. If true, this means the universe's end is not a singular event but part of an ever-expanding network of universes. The observable universe, with its finite horizon, represents just a minute portion of this multiverse, leaving vast realms permanently beyond our reach. Multiverse theories also intersect with quantum mechanics and string theory, offering speculative but mathematically rich frameworks for exploring the cosmos. However, these ideas face the challenge of testability. Observing or interacting with other universes, if they exist, may be fundamentally impossible given the constraints of our physical laws. Nevertheless, some scientists suggest that indirect evidence, such as anomalies in the cosmic microwave background or gravitational wave patterns, might hint at interactions between universes. Returning to the question of the universe's end, it becomes apparent that our understanding is constrained by the limits of human perception and the frameworks of our current theories. Whether the cosmos is infinite, bounded, cyclic, or part of a multiverse, the nature of its ultimate fate, or lack thereof, remains a profound mystery. However, this mystery fuels scientific and philosophical inquiry, pushing humanity to refine our understanding of the cosmos. One certainty persists: the journey to comprehend the universe is as infinite as the cosmos itself. As we refine our tools, theories, and observations, each discovery unveils new questions. The universe, in its grandeur and complexity, reflects the boundless curiosity of the human spirit. Whether through the lenses of telescopes or the equations of theoretical physics, we continue to explore, question, and marvel at the universe's wonders. And as we probe these cosmic mysteries, remember, the quest for knowledge is as eternal as the universe itself. To stay updated on these fascinating explorations, don't forget to like, subscribe, and join us in our shared journey through the cosmos. Thanks for exploring the cosmos with Space Lab. Like, comment, and subscribe to join us as we uncover the universe's greatest mysteries. Until next time, keep looking up and stay curious.